In this lecture, we will learn how to analyze a continuous beam using slope deflection method. We take the question asked in Anna University end semester examination in April 2016. That is, a continuous beam ABC is fixed at A and simply supported B and C. The span AB is 5 meter and carries a concentrated load of 80 kilonewton at its midspan, and the span BC is 8 meter and carries a uniformly distributed load of 12 kilonewton per meter. Take the flexural rigidity for portion AB as EI and that for portion BC as 2 times EI. Analyze the beam by slope deflection method and draw the shearing force and bending moment diagrams. So graphically, this is the problem. So we have one support fixed, another two supports simply support, and this portion is of EI cross section and this portion of 2EI, double time the stiffness of the problem. Then it is subjected to 80 kilonewton its midspan. This is 12 kilonewton per meter UD. So first we have to formulate slope deflection equations at each support for each span. So in general, the expression for slope deflection equation is MAB is equal to 2 times EI divided by L into 2 times theta A plus theta B minus 3 delta divided by L then plus fixed end moment MFA. Similarly for MBA, 2 EI by L into the whole theta A plus 2 theta B minus 3 delta by L plus MFB. Now we will consider each member separately. First member A. So to find out the fixed end moment, we consider both ends are fixed. So A and B are fixed. So due to central load or central point load, we will have some support moments as so WL by 8. At support A we have anti-clockwise direction, which is negative moment. At B we have clockwise moment, which is positive. So in the problem, support A is actually fixed. That means it will not rotate. Therefore, theta A, rotation of A is equal to 0 because of fixed support. Then there is no sinking of supports. In other words, there is no relative difference in support level. That means delta is equal to 0. Now we will calculate the fixed end moment at each support. MFAB is equal to minus WL by 8, which is equal to minus 50 kilonewton meter. Similarly, moment FBA is equal to plus WL by 8, which is equal to plus 50 kilonewton meter. So we have all the data to formulate slope deflection equation. So next we will write slope deflection for each support. So 2 EI by L, here L is equal to 5 meter into 2 times theta A, but theta A is equal to 0, in this case, and plus theta B minus 3 delta by L, but delta is 0 in this case plus but minus here minus 50. So which is equal to 2a by 5 into theta b plus 50. Similarly, MBA is equal to 2a by 5 into theta a plus theta b minus theta delta by L plus 50, but theta a and delta is 0. Therefore, 4EA by 5 into theta b plus 50. So next we will consider member BC, and both supports are fixed to calculate the fixed end moment. So therefore, W is divided by 12 due to the UDL. Okay, but this section is of 2 times EA stiffness. Therefore we have to keep in mind. Okay, very carefully while writing slope deflection equation. Here also delta is equal to 0. There is no relative settlement in supports. Therefore delta is equal to 0. But both supports are similarly support. Therefore we have rotation theta b as well as theta c. And fixed moment MFFC is equal to minus WL squared by 12 because no negative moment, therefore minus 64 kN. Similarly, MFCB is positive moment, so plus 64 kN. Therefore, the slope deflection equation becomes MBC is equal to EI into theta B. Okay, here remember 2 times 2EA. Okay. By L into theta b plus theta c, this is 0. So EI into theta b plus 0.5 EI theta c minus 64. Similarly, MCB is equal to 0.5 EI theta b plus EI into theta c plus 64. So this is the slope deflection equation for member BC. Now we will apply equilibrium equations at each joint. Therefore, first joint B, sigma MB is equal to 0. There is algebraic sum of all the moments must be equal to 0 in order to be the joint in equilibrium. Therefore, MBA plus MBC is equal to 0. Already we have the expression, slope deflection expression for MBA and MBC. That we have to write here and equal to 0. So equating these two, we get finally 1.8 times EA theta B plus 0.5 EA theta C is equal to 40. So this is the first expression, equilibrium expression we have. Similarly, at joint C, all the moments, algebraic sum of all the moments must be equal to 0 because of similarly supported ends. Okay, therefore sigma MC is equal to 0. Here we have only one moment expression MCB, which would be equal to 0. Therefore 0.5 EI theta B plus EI theta C is equal to minus 64. This is our second expression. So now we have two expressions and two unknowns, theta B and theta C. Therefore we can solve these two simultaneous equations. Solving the equations, we get EI theta B is equal to 920 by 31. EI theta C is equal to minus 2444 over 31. So these two values we have to substitute back in moment expression to get the moment value. Okay, so substituting these values, we get MAB is equal to minus 38.13 kN, MBA is equal to plus 73.74 kN, MBC is equal to minus 73.74 kN, MCB of course we get 0. So in order to draw the bending moment diagram, we need also the moments in the case of simply supported. Therefore, for spans AB and the BC, so this is the expression, this is the scenario. Okay, so central load we have 80 kN, therefore maximum moment at this point under the load, which is equal to WL by 4. So it is 100 kilonewton meter. For span BC we have UDL. So maximum moment occurs at midspan, which is equal to WL squared by 8, which is equal to 96 kilonewton meter. First we draw the support moment, then we will overlap the simple support moment. Okay. So this is the simple support moment. AB span has point load, therefore linear variation, and span BC as UDL, therefore non-linear variation. Okay, parabolic. So the final net moment is this portion, which are not crossed by each other. Okay. So this is the positive moment, and the red portion the negative. Now we will try to draw the shear force diagram. So to draw the shear force diagram, we have to determine all the reactions. Therefore again we will consider the free body diagram of each span, then we will analyze separately to find out the reactions. So here we consider the reaction at B as RB1, because we will have another part of reaction RB from span BC as RB2. Putting together RB1 and RB2 will be the resultant or net reaction RB at support B. Now taking moments about support B, or we can say take either support A or B, whatever it is. Okay. In this case we take moments about it. That means sigma MP is equal to 0. So RA into 5, which is positive direction, minus 38.13, which is negative, minus 80 into 2.5, which is negative, and again we have positive 173.74 at support B, which is equal to 0. Therefore we get RA is equal to 32.88 kilonewton. Now consider sigma V is equal to 0 equilibrium condition, which will give the value of RB1. So RA plus RB1 is equal to 80. Therefore RB1 is equal to 80 minus 32.88, which is equal to 47.12 kilonewton. Now consider the other span, free body diagram of BC. So here moment at C is equal to 0. Okay. Now taking moments about C or B, whatever. Okay. In our case, we consider the support C. Therefore, RB2 into 8 meter is a positive, minus 12 into 8 into 8 by 2 is negative, then 73.74 negative is equal to 0. Therefore, we get RB2 value as 57.22 kilonewton. So again, Considering sigma v is equal to 0 condition, we can easily find out RC value. So RC is equal to 38.78 kilonewton. Now we can draw the shear force diagram. So first, specify the reaction at support A in upward direction. Then there is no change in load. Therefore, straight line. Now 80 kilonewton is acting down. Therefore, 80 down. Now there is no change. Therefore, straight line. Now again up as RB1 goes up. Then RB2 again goes up. Okay. Then for RC value we can specify here. Then these two joints the 2 points we can join because of UDL only. Now this inclined portion. Okay, linearly varying. So this is the shear force diagram.